In this lesson, we're going to talk about one of the most important aspects of basic math that you'll need to master for the executive assessment, and that's simply linear algebra. So let's just define what linear algebra is and how you'll use it on the test. It's anything that can be represented as a line on the coordinate plane. Now, geometry in a plane sense is not tested on the exam, but linear algebra can be represented on the coordinate plane because the coordinate plane is just a physical manifestation of linear algebra, which is what the test is evaluating your abilities in most commonly when they're dealing with anything involving algebra. So a line means that there's one possible value for any variable in the equation at one time. So you can't have multiple outcomes, there's just one. And again, this will turn into word problems very quickly. So a variable is simply an unknown that can be different values pending values of the other variables and possibly constants in the equation. Now, a constant is an unknown value or known value that has a single possible value. So you might be told that k is a constant. Well, that means there's just one value of k. It doesn't change. So if you solve for k once, it's done. Other numbers are also known as constants because the value of 10 is always 10. Then we've got a sample linear equation here. We've got 4x plus 3y is equal to 84. So that has one value for x and one value for y that will dictate different values, but I can't solve for either by themselves. Now, strategic implications here, you want to always attempt technical algebra first for problem-solving questions that have clear algebraic expressions. But you'll want to abandon that approach as soon as it stops being both apparent and simple to you. So the apparent, remember, means that you can set up the math, and simple means that you can solve it. And if the algebraic expression is given automatically and not obscured by some words, that's especially an indication on the executive assessment that you may need to do some technical algebraic manipulations. Now, you'll want to rely primarily on algebraic translations for data sufficiencies and especially word problems. So in technical algebra, when you see it in problem solving, you might have alternative tactics. When it comes to technical algebra on the data sufficiency side, you really want to lean into doing the technical manipulations because that's going to be a more efficient and clinical way to determine sufficiency rather than trying to plug in a bunch of values. You especially want to do this with word problems by turning all of the unknowns into as few variables as possible. But also beware of solving for unsought individual variables. So think about it this way. If I'm being asked for what 2x plus y is, I want to try to manipulate my equations or expressions directly to 2x plus y. I don't want to solve individually for x and then individually for y and then plug those back in to solve for 2x plus y because that adds extra steps that you may not need to complete because of the sought value being that composite of 2x plus y. So definitely beware of solving for individual variables when you're being asked to find a combination of some variables. Now, let's talk about the algebraic order of operations. And this is really just for the executive assessment. Don't go into your MBA course later on and try to use this explicitly. It's an oversimplification, but remember that the executive assessment is asking you to do all of these questions in just under 2 minutes, 10 seconds. So you can use this simplification for this test. So first, you want to eliminate fractions or decimals by multiplying the full equation by either the least common denominator or a power of 10. It's quite simply a fact that human brains are more equipped to solve things when they're integers rather than when they are fractions or decimals. So the first thing you can do is get rid of your fractions or decimals by just multiplying your entire equation by either the least common denominator or a power of 10, because that will get rid of the decimal by shifting the decimal to the right, however many places you need to, and by eliminating the denominator of any fractions you might have. Then, and it's only a then, because there's a little bit of flexibility here, you want to work to efficiently isolate for the sought value or values using the 4 basic functions following the PEMDAS order. So, of course, PEMDAS is parentheses, exponents, multiplication, division, addition, and subtraction. Remember that multiplication and division are ultimately at the same level. So if you have multiplication and division, you just go left to right. Same thing with addition and subtraction, because adding 4 is the same as subtracting -4. So those are at the same level as well. So you'll just have to go left to right if you've got addition and subtraction in order at the same position in your manipulation too. So then our last step is going to be to eliminate exponents or radicals by appropriately raising or rooting the full equation. You leave this until the end because otherwise you're going to have to do a whole lot of distribution and the square rooting gets weird and the exponents get weird. You're going to just leave this until the last bit, and hopefully your radical is as isolated, your radical or exponent is as isolated as possible on one side of the equation at that point. Now, let's take a look at an example. So we've got 1/4 times the quantity 2x squared plus 8 is equal to 34. So we know that first we're going to get rid of that fraction. We're going to multiply the whole equation by 4, and we get 2x squared plus 8 is equal to 30 times 4 plus 4 times 4, or 136. Again, always look for those mental math shortcuts. I know 30 times 4 is easy. I know 4 times 4 is easy. Just add those two things together rather than trying to do 34 times 4 at the outset. Then we're just going to subtract 8. We then have 2x squared is equal to 128. Then we've got to divide each side by 2. We discover that x squared is now equal to 64. So we finally get to the last part where we have to eliminate the exponent by square rooting that full equation. And we discover that x is equal to either positive 8 or negative 8. And this is an important thing as well. Remember that when you square root, you have to account for both the positive and the negative outcomes potentially. Because, of course, 8 times 8 gives 64, but so too does negative 8 times negative 8. So now that we've seen how to solve one individual linear equation, we can just take a look at what is known as a system of equations. So a system of equations is going to be used to solve for either an individual variable or some combination of variables with multiple equations. And these can be used to solve for the exact individual variables if the number of provided equations is equal to the number of provided variables. And we've talked about this in other lessons as well. If I'm trying to solve for one individual variable, one unknown, I need one equation. If I'm trying to solve for two unknowns, I need to have two equations. If, however, I'm trying to solve for 74 unknowns, theoretically, I need 74 unique equations. So if you have the same number of variables as equations, systems of equations might be the most efficient path to solving. And these can also possibly be used to solve for a proportion, even if the number of variables is greater than the number of provided equations, because you might be able to put x over y or a over b. So recognize what you're being asked for, because you might be able to solve for some combination, even if you're not able to determine definitively what the variables themselves are. So let's talk about the strategy here. You want to always articulate your information, especially in word problems, consistently, but with the fewest number of variables possible. So if I'm being asked about something involving the number of months in a year, well, if I go X months, I know the remaining months is 12 minus X, whatever it is. I don't want to say the number of months is X and then the number of remaining months is Y when I know the remaining is just 12 minus however many were selected out of those months. Similarly, you want to recognize that substitution is going to be the long way to solve a system of equations on the executive assessment. Can you substitute and then plug everything back in? Absolutely. Is it the most efficient way to solve? Most likely not for this test. So be prepared to apply a system of equations and solve for one or a combination of variables directly using said system rather than potentially using your default position, which for most folks, if they're out of practice with algebra, is to substitute. Solve for one, then substitute, solve for the other. Yes, you can do it, but it's probably not the most efficient path. And instead, you're going to seek savvy ways to stack the equations and eliminate a full variable by finding a common multiple and adding or subtracting those full equations. And we'll see how that looks here in a moment. So to solve for an individual variable with a system of equations, first, stack the equations vertically aligning the variables. Then you want to multiply to find a common multiple of the not sought variables. And this is important because we're going to eliminate the variable that we're not looking for. And last, we're going to add or subtract those equations to eliminate all of the variables that are present except for the sought variable, and then solve for that specifically sought variable or combination thereof. So, for example, if we're being asked, what is the value of y if 5x plus y is equal to 45 and 2x minus 6 is equal to 2y? We can solve this using a system. So we just stack those equations first. We've got 5x plus y is equal to 45, 2x minus 6 is equal to 2y. So then we want to get rid of our x's. And we do that by multiplying the top equation by 2 and the bottom equation by 5, because then we've got equivalent equations and a similar or an identical coefficient for our x's. We've got 10x on the top equation and 10x on the bottom equation, because when you multiply the top equation, 5x plus y equals 45, by 2, you get 10x plus 2y is equal to 90. And if you multiply your bottom equation by 5, you get 10x minus 30 is equal to 10y. So now we can simply subtract these equations from each other to eliminate the x variable entirely. And we're left with 2y minus 30, which becomes a plus 30, is equal to 90 minus 10y. Then all we have to do is add 10y and subtract 30 from each side to discover that 12y is equal to 60. We then divide by 12 and we discover that y is equal to 5. And this, in the moment, is going to be a much more efficient path to solving rather than solving for x, plugging back into y, and then solving, or plugging back in for x and then solving for y. So, moving along, you can also solve for proportional values with linear equations. So first, again, articulate the information algebraically. Then you want to work to isolate for those sought value or values in terms of the other variables. So for example, we've got James has invested in 3 funds, X, Y, and Z. If 10% of the total he invested in X is equivalent to 30% of the amount he invested in Y, and the amount he invested in Z is half what he invested in X, what fraction of his total investment is in fund Z? This is absolutely the kind of harder level executive assessment, quantitative and honestly 2-part analysis style question that you might even see on the integrated reasoning section. There's just a lot to go through, but if you know how to do it and do it deliberately, it's not as difficult as it seems at the outset. So we start just by articulating what the problem says. So it says 10% of the total he invested in X, so that's 0.1x, is equivalent to 30% of the amount he invested in Y. Well, that means 0.1x is equal to 0.3y. And the amount he invested in Z is half what he invested in X. So that means 1/2 X is equal to Z. And we know that our total investment is whatever he invested in X, whatever he invested in Y, and whatever he invested in Z. And we just articulate that using the variables X, Y, and Z. So we have these 3 equations, but we can't really solve for anything because the total functions as its own variable as well. But we want to set our total in terms of X and Z only because we're comparing X to Z. And we can do that by saying that X is X plus 1/3 of X plus 1/2 of X is going to be equal to X plus 1/3 of X plus Z, because we know that if we multiply that very first equation by 10, we discover that X is equal to 3y. So that means that Y is equal to 1/3 of X. So now we've set the Y variable in terms of X. And the left-hand side is all in terms of X, but on the right-hand side, we keep our Z so that we can relate X to Z as was being sought by the problem. So then we just have to combine our structure, and we can do that most efficiently by multiplying by 6 to eliminate all the fractions in one go. So we end up with 6x plus 2x plus 3x is equal to 6x plus 2x plus 6z. We combine the like terms, we get the 6x plus 2x plus 3x on the left-hand side to equal 11x, and that's going to be equal to 8x plus 6z. So then we can see that 6z is going to be equal to 6 times 1/2 x, or 6z is equal to 3x. And that's exactly what we saw, right? Is that the 6 times 1/2 x is equal to 3x, as well as if we just subtract the 8x from the 11x, we get the exact same thing. And that is kind of your check as well to make sure that your algebraic manipulation is on point. So then we know that 3x out of 11x is what we have, because the total on the left-hand side was 11x. That's the total all in x's. And we know that z being equal to 3x, or the 6z, the total, means that the z investment is 3/11ths of the total, and that's how we could solve this problem without having to plug in anything, and by technically manipulating to just get the 2 variables in terms of each other that we needed. Now, let's move on over to the whiteboard and take a look at a couple of examples together and see how you would be able to execute on these types of linear algebra problems that are so integral to the quantitative and potentially the integrated reasoning sections of the executive assessment. Here we have a sample problem solving question. So we'll set this up the same way we do every time. Answer choices listed vertically for possible process of elimination with a little line over top for what we're being asked to solve for. And in this case, we've got real numbers. So we'll write those out too. So we've got 185, 220, 110,000, which I can just shorthand as 110K, 185,000, which I can shorthand as 185K, and 220,000, which I can shorthand as 220K. And do note that there's a big spread in my answer choices. I should be able to either get down to the ones in the 100,000s or get down to the two that are only in the hundreds. There should be a really apparent logical estimation opportunity at some point in this problem just because of the organization of the choices. So we skip to the end, figure out what we're being asked for, and we can see we're being asked for what is the variable cost per widget at Sasquatch Corporation. So I'm just going to be asking myself for the cost per widget. And since we're looking for this as a variable, some unknown, we'll just call that our x. Now we start reading from the beginning, taking notes as we go, and if we can build algebraic expressions, we should do so. So at the top, Sasquatch Corporation's total monthly expenses are equal to a fixed monthly production cost. So we know that our total expenses, in EXP we can write that, are equal to a fixed monthly cost, and we can call that y. So y is going to be equal to the fixed cost plus a variable production cost that is directly proportional to the number of widgets the company produces that month. So that's going to be plus my x times the number of widgets. And I've got the equation basically figured out from the word problem. And if this is the case, we'll just start filling in the algebra as we go. So if Sasquatch Corporation's total monthly expenses are $405,000, so we can say $405,000 in a month in which it produces 1,000 widgets. Okay, so that's going to be equal to our monthly expense of y plus 1,000 widgets times the variable expense of x. And $515,000, so 515,000, in a month in which it produces 1,500 widgets. So that's our y plus 1,500x. And if that's the case, we now have two variables and two equations, which means we can solve this as a system. So what we'll do, rather than substituting one of the two for the other, let's just solve for x directly, because we already have the same number of y's in each equation, one y. So I can just subtract the two equations from each other to cancel out our y's. And 515,000 minus 400,000 is going to give me 115,000. Minus 5,000 will give us 110,000. And that is going to be set equal to our 1,500x minus 1,000x, which leaves us with 500x. And sure enough, at this point, we know that all of the 100,000 options are way too big for our possible variable x. So we can get rid of all of those even if we got stuck at this moment. Now, recognize as well that we once again have a situation where long division seems more difficult than it is. First, just cross out the extra zeros for the 100 and simplify my division of 5 here. So we're going to have 5 going into 1100 now. 5 goes into 11 two times. 2 times 5 is going to be 10. Subtract that out, we get another 10. 5 goes into 10 exactly 2 times, and we just have a 0 left over. So our cost per widget, sure enough, is $220 per widget. And there is the solution for this word problem algebraically in as few steps as possible using a system of equations. So now let's go ahead and take a look at how a system of equations might be used for a data sufficiency. So same general setup as always. This time we're being asked for a specific yes-no answer. Is y equal to 0? And we'll just put y/n, since it's a yes-no format, box that off as what we're being asked to solve for. And what we know we need is one equation for y alone, because if we get another variable, that's not going to allow us to solve for y alone. So condition 1 says that 5x plus y is equal to 15. Well, Could y equal 0? Sure, if x is equal to 3, but we don't know what x is. So this has two variables in one equation. Can't solve. So we can eliminate answer choices A and D because condition 1 by itself is not sufficient, and we're left with our options as B, C, or E. Then condition 2 tells us that 2x minus 6 is equal to 2y. Now, again, I know that 2x is equal to 2y plus 6. I've got one equation for two variables. I can't solve for either because, again, if y is equal to 0, then x is equal to 3, but we don't know that just yet. So we eliminate choice B because 2 by itself is not sufficient either. Now, if we combine the two equations, well, let's multiply the top equation by 2 and our bottom equation by 5 to get the same number of x's by way of a common coefficient. So the top equation, by distributing that multiplication of 2, would become 10x plus 2y is equal to 30. And then the bottom equation would become 10x minus 30 is equal to 10y. So now I can just subtract the two equations from each other, and we discover that 10x minus 10x cancels out the x's. We then have 2y minus 30 is going to be 2y plus 30 is now equal to 30 minus 10y. And if we add 10y to each side, add 10y to each side, subtract 30 from each side, we discover that 12y is equal to 0, which means that y itself is equal to 0, and the answer is always yes. Thereby, the combination of the two conditions is sufficient to determine a definitive answer. So consider system of equations or systems of equations as you work through algebra, because those will help you to most effectively solve for variables or combinations of variables when you have more information. And remember that ultimately the executive assessment is an exam that's trying to test your efficiency at problem solving. So by using these tools that we've talked about in this lesson on some practice problems, you'll get better at effectively and efficiently deploying algebra as a method of problem solving to excel at this exam.